All right, welcome to The Explainer. Today, we're going to talk about something so out there, so profound, that it literally keeps one of the world's most famous astrophysicists up at night.
Yeah, I'm talking about Neil deGrasse Tyson. He said, I still lose sleep over this fact, and I want you to lose sleep too. So, challenge accepted. Let's see if we end up staring at the ceiling tonight.
So, what's the big mystery here? What could possibly be so earth-shattering that it robs an expert on the cosmos of his sleep? That's what we're here to find out. Let's get into it.
Okay, so to really unpack this, to get to the core of what's keeping Dr. Tyson up, we've got to go back. We have to start with the man himself, Albert Einstein, and his completely revolutionary ideas about everything, about space and about time. See, Einstein's big breakthrough was realizing that time isn't this constant ticking clock for everyone in the universe. Nope, it's relative. And he found there are two main ways you can bend it, or slow it down: speed and gravity. The faster you zip through space, or the stronger the gravitational pull you're in, the slower time passes for you compared to everyone else. So first up, back in 1905, he just drops this bombshell on the world of physics called the special theory of relativity. And the big idea here is that your speed through space directly messes with your time. So if you're whizzing past me in a super fast spaceship, from my perspective, your clock is literally ticking slower than mine. And this isn't some illusion, it's a real fundamental property of how our universe works. But he wasn't done. 10 years later, he comes back with the general theory of relativity. And this is where he adds gravity to the picture. He figured out that gravity isn't some invisible force pulling things down. It's actually the curvature of space-time itself. Think of it like a bowling ball on a trampoline. The heavier the object, the more it warps the fabric of space and time around it. And the deeper you are in that gravity well, the slower your clock ticks. Okay, I know what you're thinking. This sounds like wild, theoretical stuff, right? Stuff for blackboards and equations, but it's not. In fact, there's a good chance you use this mind-bending theory today, maybe just to find your way to work. Yep, I'm talking about the GPS in your phone. So get this, the satellites orbiting way up above us are in a weaker gravitational field than we are down here on the surface. That means, according to Einstein, their clocks actually run a tiny bit faster than ours. Now, it's a super small difference, but if we didn't correct for it, your GPS would be wrong by several miles every single day. So engineers are constantly using Einstein's equations to adjust the time, just so that little blue dot ends up in the right place.
And that's the key takeaway here. This isn't just a theory in a book. It is a measurable, verifiable fact about our reality, a fact we rely on every single day. Your GPS is basically a constant, global experiment proving that Einstein was right. It's the real deal. All right, so if that's what happens with satellites just orbiting the Earth, what happens when we really put the pedal to the metal? What happens when we push this to the absolute limit? I'm talking about getting close to the ultimate speed limit of the universe.
Now, the crazy thing is, this effect isn't a straight line, it's exponential. The closer you get to the speed of light, the more time dilation just goes completely haywire. At 90% the speed of light, time slows down a lot. At 99.9%, it slows to a crawl. For you, maybe only a few years would pass, but you'd come back to an Earth that's centuries, even millennia older.
Obviously, we can't build a spaceship that goes that fast. Yet. But we can do the next best thing. We've got these incredible machines, particle accelerators, that can take tiny subatomic particles and whip them up to those unbelievable speeds.
And the perfect test subjects for this are particles called muons. You can think of a muon as a perfect little tiny natural clock. See, they're unstable, and they decay, they fall apart after a very, very short and very predictable amount of time. If one is just sitting still, we know exactly how long it's going to live. Okay, so here is the slam dunk proof. A muon at rest lasts for about 2.2 microseconds. That's its lifespan. But when you take that same muon and accelerate it to nearly the speed of light in a particle accelerator, guess what happens? It lives way longer. And not just randomly longer, it lives for the exact amount of time Einstein's equations said it would. It is undeniable physical proof that time itself stretches. And this brings us to the final piece of the puzzle, the big one, the idea that actually keeps Neil deGrasse Tyson awake. We've talked about what happens when you get close to the speed of light, but what happens when you travel at the speed of light? So let's imagine a journey, a really, really long one. Picture a single particle of light, a photon, being born at a star near the center of our galaxy, the Milky Way. Now, from our perspective here on Earth, that journey takes an enormous amount of time, 30,000 years. That photon started its trip when woolly mammoths were still a thing. That's how long it takes to get to us. But here is the absolute mind-bender. What about from the photon's point of view? For the photon itself, traveling at the universe's unbreakable speed limit, how long was that trip? That 30,000-year journey, how long did it feel? The answer, 0. Not a second, not a millisecond, nothing. From the photon's perspective, the instant it was created and the instant it hits a telescope on Earth are exactly the same moment. For a photon, time doesn't pass. At all. It stands completely still.
And that is the fact that blows Neil deGrasse Tyson's mind. Think about it. For that particle of light, there was no journey. The beginning and the end happened at the same time. It didn't travel for 30,000 years. It didn't age. The entire history of that trip, the vastness of space it crossed, from its perspective, it never happened.
So this isn't just some fun little science quirk. It's a fundamental truth about the nature of reality. And it leaves you with this unsettling question. If something we think is so constant, so absolute as the passage of time, is actually completely relative, then what else about our reality is just a matter of perspective? What else do we think is solid fact that's really just flexible? Good luck sleeping on that one.